So last time we discussed about the bending of energy bands in p-n junction as a function of x, distance from the junction. So if you have this p-n junction, this is p side, this is n side, and if you write the energy bands, conduction band and valence band, say if this is EC and this is EV, so conduction band is here, the valence band is here, and if this is well away from this junction in the p side, so this is p side, and then you have a bending out here, you have a bending out here like this. This is n side, which is far away from the junction, and then you have conduction band, quantum states here, then you have quantum states here, valence band quantum states here, and so on. So you have this kind of bending of band as a function of distance from this junction. Now we call it a barrier in the sense that if you consider an electron here, conduction electron here, and let's suppose it is in this particular quantum state, and if this electron moves towards the junction and tries to migrate into the p side, what happens to it? It can come up to here, that's fine with this energy, but then there is no quantum state available here, and so it cannot penetrate, it cannot go into the junction, into the depletion layer, and then to this p side. But if you have an electron, all these are quantum states, you have an electron in this quantum state, let us say in this quantum state. So you again take an electron in n side, conduction electron, but it is occupying a much higher quantum state. So if that turns in this direction, if that comes in this direction, then with that same energy it can really completely go into p side, it can cross the depletion layer. So for these electrons, this barrier is not surmountable, at least classically, but for these electrons this barrier is crossed, the kinetic energy will decrease, all those things will happen, but it can still cross over. So it becomes very important to find the occupancy of these quantum states. If you have conduction electrons here inside, you have many conduction electrons here, how many of those electrons are in these quantum states? How many are in these quantum states, in these quantum states, in these quantum states, in these quantum states, and so on. So the distribution of electrons in different quantum states of different energies is very, very important if you want to calculate the currents and anything. And to get that distribution, how many electrons are in these energies, how many electrons are in these energies, and so on, you need a very important concept, a parameter which is known as Fermi energy. Written as EF. So I'll write a function which is known as Fermi function, and then I'll tell why I am writing this, what is the significance. This is f, let's call it f, small fe. It's a function of energy, and it is written as 1 over 1 plus e to the power e and then minus ef and then divided by kT, Boltzmann constant times temperature. This particular function represents the probability that an electron will occupy a quantum state at this energy. Okay, so I repeat, you have these quantum states, but and each quantum state can be occupied by an electron or it can be empty. No two electrons can go in one quantum state. So if I ask that, okay, this is the energy, at this energy I have a quantum state, what is the probability that an electron is occupying this? So So that probability is given by this function. It depends on temperature, and this is the energy at which this quantum state I am asking, and this is the parameter. This EF, Fermi energy, is the parameter which you have to keep same. This quantum state, this quantum state, this energy, this energy, this energy. So as a function of energy with a fixed EF and at a fixed temperature, you can calculate the probability. So this Fermi function gives you probability that a quantum state at energy E is occupied. Now if you plot this function, first let us plot it at t equal to 0, capital T equal to 0, and see what happens. If you plot this function f E here and E here, and suppose this is EF, and suppose t is 0, k. So if t is 0 and this is in denominator, so this will be infinity, okay, infinity. And if E is less than EF, it will be e to the power minus infinity, and e to the power minus infinity is 0, so this function will be 1. So for all energies less than EF, this function will be 1. So that means if you are at 0k, then all energies, all quantum states with energy less than EF will be occupied by the electrons. Probability is 1. And if E is greater than EF, then it is e to the power plus infinity, which is infinity, and this probability will be 0. So the function here is 0. So that's the kind of function at 0 Kelvin. But if you raise the temperature, if you come at say room temperature where K into T is 0.026 electron volts, and then you have some EF and at some energy you are asking, what will happen? This gets modified, but still the modification is close to this EF only. So if this is EF, then the function looks like this. The function looks like this. So it's again close to 0, much beyond this EF, much beyond this EF, this is close to 0, and well before this EF it is almost 1. And whatever is the change, it doesn't sharply fall, it falls gradually, but that change is only in a small region, and this region will be few times kT. The order of this width will be in kTs, few times this kT. So that's the kind of thing. So if you are say 100 kT times to the left, probability is almost 1. If you are 100 kT times on the other side, the probability is 0. But then if you are say 2-3 kT times this side or that side, then you can have this probability. Okay, so now let us use this function to get probabilities in intrinsic semiconductor, p-type semiconductor, and n-type semiconductor. So in intrinsic semiconductor, we say that you have small number of electrons here, only because of thermal thing, some electrons jump from there to there, and you have some holes here. Where is the Fermi energy? The Fermi energy is, this is intrinsic. So Fermi energy is almost at the middle. This is EF. So these quantum states are also far away from here. Okay, far away means this is for silicon, for example, this gap is 1.12. So half the gap will be 0.56 electron volts. Right, and kT is at room temperature 0.026 eV. So this is 0.56 eV and this is 0.026 eV. So it's far away. and therefore the probability that an electron will be here in this quantum state is very, very small, and that is why you have very small number of electrons which are able to reach here. And for holes, the probability, once again, if you look at here, again this is much below EF. So the probability of occupation is very close to 1. You are in this region, it's very close to 1. So probability that it is not occupied, which is 1 minus Fe, so that there is a hole there, that probability is again very, very small, and so only few holes will be there, much less number of holes will be there. So that's the kind of picture when you have intrinsic semiconductor. And if you have a p-type semiconductor, what happens? If you have p-type semiconductor, you know, you have the conduction band here, and you have valence band here, and you have many holes. And few electrons. So where do you think is the Fermi energy? The Fermi energy is close to this EV. So that this is close, so you are close to the Fermi energy, slightly below this, so slightly left to it, you are somewhere here. The probability is less than 1. The probability that there is an electron is less than 1, and therefore there is a probability that hole will be there. If you are here, that probability is very small, but if you are here, there is some probability. If you are right at EF, the probability is half. Okay, right at EF, if you put E equal to EF, then you get this e to the power 0, which is 1, so 1 by 2. So if you are right here, the probability is half, and if you are close to it, okay, the probability is not half, but still sizable probability. So lots of holes are here. Very few electrons are there, even less than this intrinsic case. Okay, you know that when you put this p-types impurity, then not only that, you have lot number of holes, this electron Ne, that also goes down, because you know that Ne into NH is equal to Ni square. So if this increases, this decreases. In this picture, since we have gone even far away from this Fermi energy, initially the Fermi energy was in the middle, so we were this much away. Now you are this much away, so the probability has again decreased, and you have much less number of electrons here. So here the Fermi energy is like this. Whereas if you have n-type semiconductor, what happens? In n-type semiconductor, you have lot number of electrons, conduction electrons, and very small number of holes. So here the Fermi energy is close to this EC, so that it's close to Fermi energy, you are close to Fermi energy, slightly above that, so the probability is quite sizable. Probability of occupation of these quantum states by electrons is quite sizable, so you have many electrons here. Whereas these holes, these quantum states, they are far away from this, and therefore it's very small, and you have only small number of holes here. Okay, so that is how, so this probability is almost 1 minus Fe is very small, and therefore very small number of holes are there. So this is the picture. Now for any given system which can interact with each other, parts of which can interact with each other, and it is in equilibrium. Equilibrium means nothing is changing as a function of time. Things are happening, the dynamic things are happening, electron holes are being generated, and recombination, all those things are happening. This side electrons are going to those side, the holes are, anything is, but as a function of time, things are having same values, that is thermal equilibrium. So once the system is in equilibrium, it has to have only one Fermi energy, and therefore when you make this p-n junction, when you make this p type and n type on the same wafer and then they can interact, in that case what happens, this Fermi energy and this Fermi energy has to be the same. So this whole thing has to be lifted, or this whole thing has to be brought down, so that this line matches with this line. So in this picture we have done that. In this picture your Fermi energy will be somewhere here. Your Fermi energy will be somewhere here. Okay, so for that p type it is close to the valence band edge, for n type it is close to the conduction band edge, and so on. So this is it. And once you know this EF, then using this you can calculate what is the probability of this quantum state being occupied, and this quantum state being occupied, and this quantum state being occupied. So if you have let's say 10 to the power let's say 16 electrons per centimeter cube here in this band, you have doped these many electrons are there, conduction electrons are there. So how many of them will occupy this one, how many of them will occupy this one, and so on. You have one parameter. The probability of occupation of this one is given by this expression, this probability of this, probability of this, probability of this. So you put different energies E and you can get the probability. So as this function shows here, if I draw this once again here, you can see that if this is EF, then the probability of these states will be large, occupation of these states will be large. As you go away and away from EF, then the probability will decrease. But that's not exactly the number of electrons which are there in this range. Suppose you take a small dE here. These quantum states are very closely packed with each other. So one by one quantum states I cannot discuss. So if you take a width dE and then number of quantum states will be there, and how many electrons will be there in these quantum states in this energy. If you need this probability is needed, yes, but something else is needed. Something else is also needed. What is that? That is how many quantum states are available here. The quantum states are not uniformly spaced here to here. You have a distribution of quantum states. The probability at the bottom of this conduction band is largest, but then the number of quantum states here is smallest. You have very few quantum states available. So although the probability is very high, but then the number of quantum states is very small in this dE. In that case, the number of electrons will be very small in this dE. Whereas if you go up here, the number of quantum states in this dE is very large as compared to this. But then the probability is very small. So to get the actual number, you need both the things. This is the probability, and another thing which is needed is called density of states. This is another very important concept, density of states. What is this? You take some band, some width, some energy width dE at some energy E, E to E plus dE, E to E plus dE. Consider this and then ask the question, how many quantum states are there? Number of quantum states in this dE. How many quantum states are there in this energy range? Not electrons, quantum states, occupied or not occupied. How many quantum states are there in this? And it turns out that if you make a calculation, this is proportional to or divide by dE, that will be the density of states. So if this number is dN, then this dN over dE, this quantity is known as density of state you can write as capital DE. This is called density of states. Okay. So in the conduction band, it turns out that this DE is proportional to square root of E minus EC. There are some factors here, but energy wise this is the dependence, and this is EC. Remember, the bottom of the conduction band I am writing as EC. The bottom of the conduction band I am writing as EC. So the number of states, quantum states available in a given DE, that is proportional to this. So that means as you increase E, this number is going to increase. At E equal to EC, right at the bottom of the conduction band, this number is 0. So if I plot this DE here, let's say this is energy E, and this point is energy EC, and this I am plotting DE. How will that go? This DE is proportional to E minus EC square root. So at E equal to EC, it should be 0. And then it is proportional to this. So it will go like this. This is how this density of states will change. At the bottom of this conduction band, this density is 0. That means if you just take very small DE, you will have very small number of quantum states here. But as you go up in energy, the number of quantum states is increasing. This DE is increasing, density of states is increasing. So you, in the same DE, you will have more quantum states here. So that is how it goes. You can plot this DE here also. If I draw a line here and energy is going up. So this is EC, this point is energy EC. This point is energy EC, and energy is going up here. And if density of states, this DE I am plotting on this side, right. Okay, energy is going up, and this DE I am plotting towards right. What will happen? Here is 0, and then it will see here how it is going. The slope is going down, down, down. So here it will be like this. As I am increasing the energy, here I am increasing the energy, is bending like this. So here I am increasing the energy as bending like this. So this will be your DE, density of states. And what happens to this probability on the same graph? So in this graph, if I plot, it will be like this. Say at EF it is half, and then it decreases as you go up like that. Okay. So that is how Fermi function looks like. You go away from the Fermi energy, your probability decreases, and then it becomes almost 0. So it goes like this. So look at this. The probability is decreasing. You are going up, the probability is decreasing. There is a quantum state out here. There is a quantum state out here. This quantum state has larger probability of being occupied. This quantum state has lower energy, lower probability of being occupied. But how many quantum states are here? There are more number of quantum states are here and less number of quantum states here. So if you want the number of electrons in a given DE, number of electrons in E to E plus DE, E to E plus DE, for that you have to take care of both the things, this density of states as well as the probability of those quantum states to be occupied. So you have to multiply these, and therefore this will be F of E multiplied by D of E and then DE. Okay, this gives the number of quantum states in that energy range, and this gives the probability of each quantum state being occupied. So this will be the total number of quantum states occupied, or in other words, total number of electrons, conduction electrons in that DE. So if you do that, one is increasing, another is decreasing as you go up. If you multiply them, what you will find is the following. Let me make some space here to do that. So one function is going like this, another function is going like this, and when you multiply them, what you get is some kind of a function which maximizes and then it decreases of this type. Okay. So, right at the bottom you do not have maximum number of electrons because the density of states is very, very small here. Slightly above it maximizes and then it decreases. Okay. But for all practical purposes you can neglect that variation here, and you can say that lower the energy, larger are the number of electrons, and then as you go up that number decreases. Similar will be the case with holes. Large number of holes here. The distribution will be like this. Here let me modify this. Since this is n side, the Fermi energy is very, very far away, so you have very small number of holes here, like this. The distribution is similar. You have larger number here, lesser number here, lesser number here, but total number of holes is very, very small here because this is your n side. And here you have large number of holes because this is the p side. Okay, so here you have large number of holes, and once again close to this edge you have large number. Then as you go away, because remember this is your EF, this is your EF. So from Fermi energy as you go away, this number is decreasing. But for these holes, this particular hole, if this wants to go in this side, no possibility, no state here. But if this hole tries to go this side, yes, there is a possibility, the quantum state is there, so this can migrate. Okay. So the diffusion can take place, electron going one side, hole going other side, all those things. And then there will be another very interesting thing which we call drift current, because if you don't connect a battery to the p-n junction, don't connect a cell, you cannot have a net current. So if diffusion is possible, something has to compensate for that. That is known as drift current, and that will be our next topic next day.